Next, we're gonna use breadth first search on a more practical problem. And in this problem, we're gonna search with graph. Our problem is called network delay time. It's a lead code problem 743. Now the problem is we are given an input like this. For each of these three numbers, the first number is the source node, the second number is the destination node, and the third number 1 here is the time needed for the signal to travel from the node number 2 to node number 1. So that's what we have here. We have node number 2, we have node number 1, and for the signal to travel from 2 to 1, it's gonna take 1 unit of time. With the rest of the information, we are able to construct the graph, the visual representation of the graph. For the second information, we have time for the signal to travel from node number 2 to node number 3 is 1, which is what we see here. From 2 to 3, the signal gonna take 1 unit of time to travel. Next, from 3 to 4, the signal also gonna take 1 unit of time. And that's what we have here. 3 to 4, signal gonna take 1 unit of time to go from 3 to 4. Now the 4 number we have here is the total number of the nodes. And the number 2 that we have here is the starting node. So we can see that we have 4 nodes in this graph. And our starting node is 2. Now it's worth to mention that all the edges in this graph are equal. And the question for the problem is, if we are given an input like this, we need to determine if we give our signal from a node in this particular input, that's going to be node number 2, will the signal reach all of the nodes in the graph? That's the first question. The second question is, if yes, how much time does it take for the signal to reach all of the nodes? To solve this problem with breadth first search, you can see that if we search the whole graph and we've seen all of the nodes, which is 4 here, then we can answer that yes, the signal can travel to all of the nodes starting from the given node. For the second part of the problem, if we have all the path from the starting node, we can return the path from the starting node to the furthest node, and that's gonna be the longest time it takes for the signal to get to the furthest node. And remember, we can only do that because the edges weights here are all equal. We're gonna see with another input like this one, when the edge weights are not equal, our logic doesn't hold true anymore, and breadth first search doesn't produce a correct answer. Now let's focus on this one. So we're given an input. With this input, we have a visual representation of a graph. We can translate the graph into the adjacency list because we can only apply our algorithm with the graph format that we're familiar with. So translating a given input to a graph is a foremost and necessary step to solve our graph problem. Next, let's have a look at our breadth first search implementation for this problem. First, we initialize the empty graph with the total number of n nodes. And if we print it out, this is our initial graph with no relationship just yet. Then we're gonna build the adjacency list with given time data. And if we print our graph now, our graph is now an adjacency list that describes the weighted directed graph. The graph here is actually this graph that we have here. From node 1, which is here, it doesn't point to any node. For node 2, which is here, it's point to node 1 and node 3 with the weight of 1 and 1. Remember, our node indexes is the number in the yellow. And from 3, it points to 4, which is what we have here, and the weight is also 1. And node number 4 doesn't point to anything, so it's empty. Then we have our starting node equal to k minus 1, because in our graph it's 0 indexed. Here we're gonna do a quick layer separator. It's not related to the problem, but it's important to know how to do it because this is also a very popular question asked. Then we initialize our queue with the starting node and immediately put the layer separator in there, and we're gonna see our layer are separated in a little bit. We also keep track of the node that we have seen with a set, and here we save all the paths. So a path is simply an array of nodes indexes. For example, 2, 3, 4 is a path. But remember, we're gonna use the first number of this path to save the total travel time in there. So the path actually starts as the second number of the array. Now we're gonna start our BFS. We dequeue to get the current node index. This logic here simply adds and removes layer separator. So if we uncomment this console log, and if we look at our queue here, the layers are all separated. For example, we have starting node index 1, which is what we have here. Then we have a layer separator. After we dequeue the starting node, we enqueue the node in the first layer, and we put the separator at the end of it. You can see 0, 2 is the first layer, like what we have here, the first layer. When we're finishing 0, 2 layer, and we keep dequeuing, and then we have node index 3 at the second layer. So our layer separator is gonna be placed here, and that's what we see here. And this logic that we have here, only this part, is responsible for adding and removing the layer separator that we have here. Okay, now let's get back to our main problem. We're gonna continue with our breadth-first search. After dequeuing the current node, we get the node information from the graph, and we're gonna use a temp path to update all the paths for every neighbor of the current node. We get the node index and travel time to that node, and if we have never seen this neighbor before, we're gonna add it to the scene list. We enqueue the neighbor node, and we update the path with a new neighbor node and travel time to this neighbor, and this is the logic responsible for that part. Basically what it does is when it starts from node index 1, which is here, and it's the index 0, it's gonna update the travel time to 1, and it's gonna do the same thing from index 1 to index 2 here, or index 1 to index 2 here, and it's gonna update the travel time of 1. And this is our possible paths, starting from node index 1. And when it keeps going, this path is finished, because we cannot go anywhere from here. So you can see that this path stays the same. And for this path, you can see node index 2 can go to node index 3, which is what we have here. We go from 1 to 2 and then to 3, which is this path. And when we go from the index 2 to index 3, which is here, and we're gonna add up one more unit of travel time, which is this one. So that's gonna take 2 units of travel time to go from node index 1 to 2 to 3. And then finally, if we start at this node, we have 2 possible paths. The first one is 1 to 0, and total travel time is 1, and the second one is from 1 to 2 and 3, and the total travel time is 2, which is what we have here. 1 to 2 to 3, travel time is 2, and we're gonna return the bigger travel time, which is 2. So it takes 2 units of time for the signal to travel starting from this node to go to every single node of the graph. With this particular input, breadth-first search gives a correct answer because we have equal edges weights here. But for the second setup, which what we have here, breadth-first search no longer give a correct answer, simply because of the nature of breadth-first search. Breadth-first search discovered the whole graph in this setting with only one move, from this node to this one, and from this node to this one. And each of them is gonna take 1 unit of time and 4 units of time to complete. So breadth-first search is gonna give the answer of 4 units of time for the signal to travel through all the nodes in the graph. But there's another way to reach this node, from the starting node index 0 to node index 1 and to node index 2, and the total time is only 1 plus 2, that's 3, and that's better than 4. The nature of breadth-first search simply doesn't discover the graph like this. So when given the graph with unequal edges weight, breadth-first search will not give the sorted path answer, and we're gonna learn about depth-first search to solve this problem later.